Hi and welcome to lesson of multivariable calculus. So in this class we are going to talk about multiple integrals and more specifically we are going to talk about the integrals where we need to change the order. So let's uh, take a look back at the single variable function, and if we want to find area bounded by a function, let's say this is a function f of x, and if I am interested in finding the area bounded by this curve above the x-axis, then I can simply integrate this over these limits on the x-axis, that is, let's say from a to b, and I'm going to get this area that is bounded between these two curves, right? That is the x-axis and the curve f of x. So the notion of the integral is f of x dx from the limits over these limits a to b. Now, simply, if I can carry this concept to the double integral, and we can extend this in the similar manner that if I am interested in, let's say, finding area of the curves uh, of this form, let's say if I have a this curve f of x, and one of the curve is, let's say, g of x. Now, the curves are in the plane xy plane, and the region that is bounded is between these two curves. Now, to find the limits, it's not that much easier that in case of the single variable we did. That is, we were just interested in finding the area bounded between the x-axis and the function. So it is easier in that case to just integrate the function over these limits. But in this case, what we are going to do is we have to integrate in the x direction and in the y direction as well, because what we are doing by just taking the double integral is that geometrically, if I uh, explain this concept, what we are doing is we are dividing this area that is bounded between two curves into smaller regions of this kind, right? So we are just dividing this area into smaller regions, and then we are sweeping the area in the x direction and then in the y direction, or we can do it vice versa. First sweeping in the y direction and then in the x direction. So we need to integrate this over the function, over the x-axis and over the y-axis. So the first thing that we need to do is to find the limits, right? So let's say if I have a function f of x that is square root of x, let's say this is square root of x, and this function is, let's say, g of x is x squared, and I'm interested in finding the area bounded between these two curves. Now, first of all, uh, we can integrate this function, that is integral, double integral dA, right? So the notion of this integral becomes this, that is, we are integrating this over this region. This is the region bounded between two curves. Now, to find the limits, if I am interested in finding uh, the limit in the y direction, let's say I am choosing the order of integration as dy dx, then first I need to find the limit over the y-axis. So what I need to do is just draw a parallel line, that is an arbitrary parallel line that is parallel to y-axis, and I need to keep eye on this thing, that where it cuts on the upper curve and where it cuts on the lower curve, right? So the upper limit is this curve, that is f of x is square root of x. So my upper limit is square root of x, and the lower limit is this function x squared, because the line, that is arbitrary line that is parallel to y-axis, cuts the lower curve at the that is the least point of this region. So integral goes from x squared to square root of x. This is my limits in the y direction. And now for the limits in the x direction, it's simpler because my curve is starting from this point, that is 0, and then it goes to this point that we can easily find if I am able to find this point here. Since at this point, this is the point of intersection, so both square root of x and x squared should be equal. Therefore, I can just manipulate it by taking the square root on both sides. I will get x equals x to the power 4, and then by just simply simplifying the equation, I can see that x is either 0, or from this equation I will get x equals to 1. It means that my region, the point, this point is 1, right? So we just need to integrate over this line 0 to 1. Now this gives area of this curve, right? Area bounded between these two curves. Now I can just switch the order of this integral as well by first finding the limits over the x direction and then doing it in y direction. Now let's see how can we do that. So this is my axis and these are two curves. So this is x squared and this is square root of x. This is x squared, which means this is y equals square root of x. This is y equals to x squared. Now if I'm interested in finding the limits in the x direction first, I just need to draw a parallel line to the x-axis. That will be my arbitrary line. This is x-axis, this is y-axis. Now see here that which point this line cuts on the least point of this region. So that is this point at this curve. So this is y equals to square root of x, but I need to find it x in terms of y. So it will be x equals y squared. If I take square on both sides, so it will become x equals y squared. And the uppermost limit will be this curve, that is y equals to x squared, which will give me x equals to square root of y. Now my limits are in the x direction. It will be from y squared, that is from x is equals to y squared, that is this point here, that is the least point of this region, this point, and this is the greatest point of this region. So it goes from x equals to y squared to x equals to square root of y, and then we can just find limits on the y-axis. That will be the constants. So it starts from 0 and goes here at this point. So this is, again, we already found that this point is 1 comma 1. Therefore this point is 1. So we are going to integrate from 0 to 1, and the order is now dx dy, right? Now this and this integral gives you the same value. That is the values given by these integrals are the areas that is bounded by this curve, right? So we can work in both directions, but in most of the problems, what we need to do is we need to flip the order because of the complexity of the problem. For instance, if we deal in this case, let's say we have this integral that is going from y to 1, which means that these limits are for x direction, and it's going from 0 to 1, which are the limits in the y direction, and the integrand is e to the power x squared dx dy. Now, since the function is e to the power x squared and we need to integrate this with respect to x, now the difficulty here is that this function e to the power x squared is not suitable for integration if we don't have the derivative of this exponent here, that is x squared, with this exponential function. If we have this function x here, then we can easily integrate this, but in this case it is not present. So now I can see in other way, that if I flip the order of the integration, and then we can see that we can easily integrate, because if we want to integrate this with respect to y, it is easier, right? So now, first of all, let us sketch the region over which we are going to integrate this function. Now, by the region, I mean that these curves that bounds this region. So first curve is x equals to y, which means that this line x equals to y, then it goes from x equals to y, x equals to y, x equals y to x equals 1. So x equal 1 means this line here, this line that is parallel to y-axis. So this is x equals 1, this is x equals y, and then from y equals 0, y equals 0 means this line, that is the x-axis, that is the curve y equals to 0. So this line is y equals 0 to y equals 1. So y equals 1 is this line, y equal 1, right? Now see here that which region is a common region of all the four curves. So here I can see that this region here is the common region bounded between all of these four curves. But why not this region? Because this region is outside this line, right? So we need to just consider that region that is bounded by all the curves. So this region only is the region that is bounded by all of the curves. So now we can work on this region and just flip the order of integrals, right? Now let's start the work. So let's draw the region again. So this is the region, the line x equals y, the line x equals 1, and the line y equals 1, and line y equals 0, that is this line here, and this is my region right inside this. Now this point is 1 comma 1, since the function is x equals y, this is x equals y, right? This is x equals 1, this is x equals 0. All right, now let me erase this thing. We don't need this line now. Now, if I want to flip the order of the integral, so here inside the innermost integral is the integral carrying the limit of x, but I need the limits of y here instead of x. So to find the limit of y, we just need to draw a parallel line to y-axis and just see that what is the uppermost limit and what is the lowermost limit here. So this line is cutting the curve y equals to x. So this is the maximum point of the region, and this is the minimum point of the region, which is y equals to 0, and the maximum point of the region is on the curve, that is y equals to x. So now the inner limits will be from 0 to x, that is the limits of y, and the outer limits will be for the x-axis, that is going from 0 to the point 1, because the line, this line is x equals to 1, right? So this point is 1, so these are limits for x. Now we can easily integrate this function. Now if I integrate this function with respect to y first, I'm going to get y e to the power x squared dx over the limits of y are from 0 to x, and the integral 0 to 1 will remain, right? Now e power x squared is going to remain the same, and the limits are going to be applied on y, which means that x minus 0 dx from 0 to 1, and I'm left with e to the power x squared 0 to 1 dx. And now we can see here that we have this x here, this x here, and it's e to the power x squared. So now it's easy to integrate this function, right? So if I assume that u equals x squared, so I am going to get du equals 2x dx, which means it is du over 2 equals x dx. Therefore, now my integral becomes 1 over 2 e to the power u du, which is again e to the power u over 2. And again, just substitute this thing here. Instead of u, just we can write x squared over x squared to apply the limits. So it will be e to the power x squared over 2 over the limit 0 to 1. So now this becomes e to the power 1 minus e to the power 0 over 2, which will give 1 over 2 times e minus 1. And that is the uh, solution for this integral, right? So this is the way we can just swap the order of the integrals. Now let us embark to another example. For instance, let's take this example. Here we have integral from 0 to 6. Then inside we have integral from x over 3 to 2, x is square root of y cubed plus 1, dy dx, right? Now see here, the complexity is that we cannot compute this integral y cubed plus 1 in the square root with respect to dy because we don't have the derivative of this function outside. Now we need to switch the order, therefore we need to draw the region first. So the region of the integration is this curve y equals x over 3 to y equals 2 and y equals 0 to y equals 6, which means that this line y equals to x over 3 will look like this here. This is y equals x over 3, and it's going from this to y equals 2, which means that y equals 2 is the line that is extending from y equals to 2 parallel to the x-axis, right? All right, now see the limits of uh, x here. Sorry, this is these are the limits for x, not for y. So x equals 0 and x equals 6. So x equals to 0 is this line here. That is my y-axis. This is the equation of x equals 0. And for x equals to 6, this will be the line, this one, x equals to 6. And how do I know that this line will intersect at this point? Is I can just find this point, because this curve is y equals x over 3, and this point here, this line is y equals 2, which means that this point is x comma 2, right? And since the function here is y equals to x over 3, which means that x equals 3y, therefore x equals 3y means 3 times 2. So this point is going to be 6. This point is going to be 6. So this point is going to be 6 comma 2. That means that this x equals to 6 is going to cut here. Now the common region bounded between these curves, all these curves, is this region, right? Because now this region is bounded by all these curves, right? And now I can work for this region. How do I work for this region is that now why I'm considering this region is that we have seen that y is going from x over 3 to y equals to 2, which means that this region is bounded between these two curves, right? This one y equals 2 and this one y equals x over 3, and then x equals to 0 and x equals to 6. That is these two lines, right? These two. So this is the region. Now I want to flip the order. So I need to find the limits in the x direction that should be inside. So I need to draw a parallel line. I need to draw a line that is parallel to x-axis in this manner. That is arbitrary line. And the lowermost limit is on the line that is x equals 0. So it's going from 0 to the uppermost limit of this region will be this function that is y equals x over 3, which means x equals to 3y. That will be x equals to 3y, right? And then the outer limits will be the limits of on the y-axis that are from 0 to 2. So it's from 0 to 2, and now the function is remain as it is, and the order of integral is now switched, right? And we can now simply integrate this because the integral of x is going to be x squared over 2 a square root y cubed plus 1 remains, and the limits are from 0 to 3y dy, and it's from 0 to 2. And now if I solve this integral, that is this thing y cubed plus 1 remains here, and the limits will be applied. So 3y is squared over 2 minus 0 dy over 0 to 2. Now this becomes 9y is squared over 2 times the square root of y cubed plus 1 dy 0 to 2, and this is now easily integrable because the derivative of y cubed plus 1 we can get here, that is outside. This is y squared, so the derivative of y cubed plus 1, so let us assume that u equals y cubed plus 1, which gives du equals 3y squared dy, which means that I can write here 3 over 2 integral of a square root of u du, right? So I can do this thing. So the integral square root of u gives u raised to the power 3 over 2 over 3 over 2. Outside we have 3 over 2. This cancels. And now if I again I can just write this in terms of y. So I have u raised to the power 3 over 2, which means that y, so here y equals cube root of okay, so u is equals to y cube plus 1. So I can write it y cube plus 1 raised to the power 3 over 2, and the limits are from 0 to 2. All right, so this will, we can apply the limits and we will get the answer for this integral, right? That is this result here, 26. So this is the final result that we get, and by applying the limits we will get this solution that is 26, right? So in this manner we can solve these problems. Now we have one more problem, that is this one, sine x over x dx dy. Again, we know that the integral is not much feasible to solve with respect to x first, so we can just switch the order by using the region that is given. So the limits are from x equals to y to x equals to 1, and from x equals to 0 to x equals to 1. Therefore we can draw the region, which will look like this, and then simply finding the limits for y, we can draw a parallel line to y. This is the uppermost limit, this is the lower limit, so the limit will be from 0 to y equals to x. So the upper limit, so y equals to x, and the outer limit is from 0 to 1. So this, in this manner we can solve this integral sine x over x dy dx, and now we can simply solve it by applying the integral limit from 0 to x dx 0 to 1. Now if we apply the limit for y, we will get sine x over x multiplied by x minus 0 dx from 0 to 1. So this x and x cancels. Now sine x dx is easily integrable from 0 to 1. So this is the way to compute double integrals for more complex regions, or if you want to change the order of the integration. So that's all for the today's lecture. So in next class, we are going to deal with the triple integrals. Thanks for watching the lesson. That's all for the time being.